Now, before we go to lunch, let's direct our thanks to Jacob Neumann from the University of Nottingham, who will tell us about the category interpretation of polarized and directed type theory.
Thank you. Thank you for the introduction, and thanks to all the organizers and all the presenters for putting on a really great workshop. I'm really excited and honored to be here to tell you about the category interpretation of polarized and directed type theory. So this is joint work with my advisor, Torsten Nottingham, and yeah, so I'm not going to have as much time as I would want to say all the technical details about this theory. So I will just kind of say my propaganda and maybe get into a few technical details. And then if you want to learn more, then I will direct you to. So I probably won't get through all the details in these slides, so you can find them there. And it's not existing yet, but so it's, I guess, a preprint at this point, but there will be a preprint, and even later there'll be an agri formalization, which is still too immature to be out in public. And so yeah, I'll refer you to that, or find us at lunch and ask. So I'm going to pick up on a theme that I think a number of others have touched on, which is this kind of idea of synthetic mathematics or synthetic theories. And in particular, I wanted to look at the difference between doing groupoid theory and category theory in a univalent setting. And so and this is probably a familiar story to most of you, that the groupoid story in homotopy type theory is very nice. This is one of the great things about HoTT, is that we can view the types of homotopy type theory as synthetic infinity groupoids. So the objects of this groupoid are the terms of the type, and the morphisms, or the one morphisms, are the identity proofs, and the two morphisms are identities of identities, and so on and so on. And so yeah, any type you can write down in HoTT is automatically an infinity groupoid. And moreover, any function you can write down in HoTT is automatically a functor. It's automatically a functor of infinity groupoids. So you can prove using path induction or the J rule that you can do this, this standard thing with applying F to get that the kind of morphism part of this functor, and you can easily prove that it preserves identities, which is REPL, and the composition, which is the path concatenation. And the point I want to make about this is that you don't have to look at F itself. You don't have to inspect the definition of F to do this, and you don't have to do this by hand. We can prove this app once and for all for every single function on every single type, and you don't have to dig into the weeds of proving functoriality or proving that or even supplying with the morphism part. It just happens kind of automatically. So this is a very nice story, a very nice picture. But on the other hand, the category theory side is nowhere near as nice, or nowhere near as convenient, let me say. So if I want to define a category in univalent mathematics, which a number of speakers, particularly yesterday, talked about, then we have to do that by hand. We have to say what the objects are. We have to say what the morphisms are. We have to check all the category theory laws by hand. If you want to define a functor between these categories, then we have to define its morphism part explicitly, and then check functoriality by hand. And of course, if we're trying to do something like infinity category theory, then this is going to be something of a problem, because we might end up doing infinite work, and we might end up in kind of some coherence hell, and yeah, there's all kinds of difficulties that we didn't have in the groupoid case, which we do have now in the category theory case. And so a kind of way of summarizing this is that in univalent mathematics, groupoids are treated as synthetic. They are these synthetic objects, whereas categories are analytic. We have to build them out using the theory. And so I think it's important to ask why. Why are these so different? And so in a certain sense, I view this as a kind of ontological scandal that these very similar kinds of things, groupoids and categories, are treated so differently by our beloved homotopy type theory. That one has this convenient formalism that we can just write things down and they're, wave a magic wand and they'll automatically functorial and compare and whatever. Whereas the other one we have to do by hand. And so what I'm claiming is that we should fix this, or we can fix, or if we can, we should fix this. And so the moral of this story is that we should do synthetic category theory if we can, which means we should do directed type theory. And so you'll be glad to hear that several authors, including our distinguished chair, have risen to this occasion and have done their duty and have come up with a wide literature, which I can't claim to have mastered in any sense, on directed type theory. And there's a number of different approaches with different motivations, and this is by no means an exhaustive list. Different motivations and different aspects of the theory. And yeah, I encourage, or I recommend many of these papers to your reading. But I think there's a little bit more that can be added. And so what I want to add to this literature is kind of two things. So first of all, I'm not aware of a directed type theory based on the formalism of categories with families. So I'm a big CWF fan, and I think they're very nice for both for technical and for aesthetic reasons. I think they're a nice formalism. I'm not aware of a theory of directed type theory that makes essential use of them. So that's one thing I think that can be added. So some of these other ones I listed have, are based on, some of them don't have a model theory, some of them are based on other kinds of model theories like contextual categories or tribes or various things like that. But yeah, I want to do CWFs. And then the other thing is this phenomenon, which I call deep polarity, which I am not aware has been addressed anywhere in the literature. And I'll say in a moment what that is, but these are two things which I think can be added to the field of directed type theory, and which might help us to do synthetic category theory. And so in particular, what I want to do is to kind of conduct the directed analog of a couple really important and landmark papers in the history of homotopy type theory that came out in the 1990s. And so that's why I have this kind of tacky 90s theme for these slides, is that, the 90s. And so in particular, I'm interested in the work of the UVA to find category for families. As I said, that's going to be the kind of model theory that that we're running with. Which one of the kind of nice technical reasons that those are convenient is that they have the form of a generalized algebraic theory, which makes it more convenient to transcribe them into a computer proof assistant. And then, but mainly what I want to talk about or hit on is this famous paper of Hoffman and Streicher, the group-wide interpretation of type theory, which what they do is they define what's called a group-wide model, which is a CWF structure based on the category of groupoids. And of course, their use for that was to prove the independence of the UIP, or the axiom K, which I'm not going to touch on today, but I think is it's an interesting question to ask: what is a directed analog of that result? And next month, so our talk has been accepted for the HoTT conference next month in CMU, and so there we're going to be doing going further and doing free-sheet semantics for directed type theory, which is I think an even more fascinating and compelling case. And that's kind of doing the directed analog of these other two kind of classic papers. Or I guess this one wasn't published, but yeah, Hoffman and Streicher's lifting growth in deep universes, and Hoffman's semantical analysis of higher order abstract syntax. So yeah, if you're able to definitely come to Pittsburgh, and we'll party like it's the directed analog in 1999. So, all right, so that's my propaganda bit. Hopefully I've piqued your interest and have given you something interesting to think about over lunch, which maybe is what you're thinking about now. But let me try to get into a little bit of the technical details of some of this theory. So I think a few authors have already introduced or assumed a notion of categories with families. So I'm not going to dive too much into the definition. But categories with families are a very nice model theory. They're very straightforward, like what is your interpretation of type theory? It's not kind of hidden in some clever encoding trick. It's very explicit. What's a type, what's a term, et cetera. And so yeah, I just included here the technical details, and there's this isomorphism we want to hold. But the point I want to get to is that the groupoid model, so going back to Hoffman and Streicher, their groupoid model is defined as a CWF. So if you go through the paper, they actually do go through the steps of defining every bit of what is this CWF. And so in particular, the reason it's called the groupoid model is because the context, the category of contexts are groupoids. It's the category of groupoids. And then the types in a context gamma are gamma indexed families of groupoids. And so this is kind of and I'm not going to go through all the details, but this is the kind of basic setup of this groupoid interpretation of type theory. And of course, their ultimate goal is to say something, is to prove this result about identity types. And so they also have to interpret other things like dependent types and identity types in order to be able to study those in this context. And so, like I said, our main idea here, our main goal here is to do for category theory what ordinary undirected type theory does for groupoid theory. And so kind of the obvious way to go about this is just to go through the literature and find places where they say groupoid and try to replace it with category. And indeed, we can do this with the groupoid model and get the category model. And so here we have the contexts are categories. Here we have our contexts are categories, and we have that a type in context gamma is a gamma indexed family of categories. And then we can go through all the other details and get that this is indeed a CWF, and it is well behaved and everything like that. But the interesting part of this is that we get some further structure on this CWF. So it's not just a CWF. There's more to it than that. And in particular, there's this really important operation that we can do on categories, which was basically invisible on groupoids, which is the operation of taking the opposite category. So for every category, if you've done basic category theory, you'll know for every category, I can take its opposite. I can flip all the morphisms around, and I get potentially a different category. And this actually rises to an endofunctor on the category of categories. And so what we want to do is we want to take this semantic, this kind of model theoretic operation. This is something that's happening on our semantics, on our model, and we want to drag it into the syntax so we can talk about it in the syntax of our type theory. And there's actually two ways that this opposite operation can be brought into our syntax. First of all, if our contexts are categories, then we can take the opposite of a context. And so I can write that as gamma minus for some context gamma. And so this is what I'm going to be called, this is what I was referring to as deep polarity, in that it's not just a polarity on the types and on the terms of the theory, but it's on like the structure of how the theory works itself. It's on the context. So it's a deep polarity. And then there's kind of a shallow polarity as well that we can. So if we view a type in context gamma as a functor from gamma into cat, then we can just post-compose it with this functor and get a new one. And so this is a kind of type negation operation. And notice that it stays within the same context. So it's within the types of in a given context, we can with this negation operation. And this is the feature that's mainly focused on in the existing literature, is this kind of shallow type negation, or the shallow polarity. And so this leads me to this definition of polarized categories with families. Is we abstract these details that we found in the category model to a kind of general structure. And so what it is it's basically the same ingredients as the CWF, so context and types and terms, But then we have this context negation operation, so a functor on context, satisfying some laws that we might want, as well as on types, a type negation operation. And if you actually dig into this theory, you'll find that well, we can go a little further with this, and we can actually get two kinds of context extension, a positive and a negative one. And so this is the formation rule for that. So this is what I'm calling a polarized category of families. And I think this is a helpful basis for proceeding with a study of directed type theory. So I'm about out of time, so I'm going to, and this is nice condition, but I'm about out of time, so I'm going to kind of zoom through the rest. The other thing we can do is we can have Hom types. So in the groupoid model, we had identity types, whereas here now they're going to be directed. They're going to be Hom types. And so this is the kind of formation rule for it. And so we think of these. So this is going to be really the essential ingredient for doing something like synthetic category theory, in that we have for any kind of two objects, then we have a type of morphisms between them. But notice that I'm making kind of essential use of these polarities in this definition. So we want to mark A naught here as appearing negatively, whereas we want to mark A here as appearing positively. So there's where we're kind of using at least the type polarity. It's not 100% clear how the deep polarity plays into some of this picture, but that's a topic for further research. And so like I said, this is going to be the essential ingredient for doing synthetic category theory. All right. Let me go ahead and wrap up. So there's a lot of other aspects of this that are interesting. We have these core types, which are kind of bivariant or appear positively and negatively. But what I really want to get to is that we can define identity morphisms in the kind of referral that goes from A to itself. I'll go into some technical details. And we can state a directed version of the J rule of path induction. And in fact, we can do two. We can kind of negatively path induct and positively path induct. And so as just kind of a proof of concept for these J rules, we can actually construct the composition of two suitable Hom types and get their composite. And so this is starting to look like synthetic category theory. There's a lot of details to work out, but hopefully the general scope of things is maybe starting to come into focus. So something like these ingredients is what would go into a directed category with families, which is a polarized category with families. So it's the basic CWF structure, and then this polarity. And then we add on, I didn't really get the chance to talk about core types, but ask me about them if you're curious. And then this morphism type former with referral and with J. So we're starting to do synthetic category theory in a homotopy type theory like system. So I'm going to go ahead and finish there. So thank you for your attention.
We have a couple of minutes for questions, so.
In this CWF of categories, did you think about pi types in that?
Yes. So there you can define a pi types in the context of in this CWF. It's tricky because you have to structure the polarities right, because of course a pi type is a kind of function like, and so it's going to kind of flip the polarities. So you do need to be careful about making the codomain and the domain having different polarities, but you can do pi types.
Okay. Maybe I'd like to see that afterwards, because I was, I've thought about this at some point, and it's just a natural definition. You want to, because of the reindexing, even before you talk about polarities, because of the reindexing, you need to do sort of like a crypto structure, I think.
Right. I think Yeah, so I think there's some details which I haven't fully worked out in terms of pi types. I know it definitely does work for like non-dependent function types, but I think this should be discussed more.
Yeah.
Yes. Any more questions?
Yeah, I've got two closely related questions. It's a little bit about let's say the connection by the work done by Paige. The first thing is I must admit because they what they've done is in particular like introduce comprehension by categories to model directed type theory. But so here you stay like in the one-dimensional case. So in what sense does it differ? And also you said like these polarities that is not really been done in the literature, but also with in that work they also do something analogously, just this op construction. What is like the difference between their approach and yours?
Yeah, so I'm not an expert on their approach, but my understanding is that approach also includes a kind of directed judgmental equality. So that complicates the story of like what's the relationship between these two different ways of approaching it. So yeah, I would like to understand that better. And I can't say that I do too well at this point. And as for your point about we're at this point we're kind of staying in the one category world, just kind of get a foothold. And ultimately my hope is to do something more like infinity category theory involving this, and kind of take this, because ultimately, of course, we want to iterate the Hom constructor and have Homs between Homs. So at this point in the you can prove a kind of you can prove that the category model satisfies a kind of not axiom K, but like axiom K1 level up. So these Hom types are going to be set in the category model. But ultimately, we'd like to get beyond that, and I'm hoping that the pre-sheet semantics are do that better, and that they don't tie us to having just set of Homs, but higher structures.
Thanks.
Yes. Hi, thanks for your talk. Have you tried to check what happens when you have some structure on the context category and how that propagates into types in that context?
Sorry, can you say what you mean by like some structure on the?
I mean, for example, like you have internal products, meaning in the context, because you have the category gamma to have products or something else. Right.
No, I don't think I've looked too much at that. So I'd be interested to hear more about that. About kind of what you have in mind there.
All right. Thanks.
Thank you. Any more questions? Okay.
Hi, thank you for the talk. I was wondering if it's the case that, so I'd expect for either one category theory or infinity one category theory that the Hom types would be sets or groupoids or something like that. Does that fall out of your formalism, or do you get like another category of arrows?
Yes, I mean, I think that was what I was trying to say a moment ago, is that in the category model, you are going to get the Hom types are some notion set. So they do kind of have the Homs between Homs become trivial. But yeah, I think the ultimate goal would be to have a theory that can accommodate the directed analog of like higher types or higher inductive types that have more interesting structure. To kind of try to model higher categories.
Thank you.
I guess if there are no further questions, then it's time for lunch. So let's thank the speaker again.